Please subscribe my channel. Okay, it's a request. Our today's topic is Zener diode, how it acts as regulator, or you can say how it acts as a stabilizer. Zener diode as regulator, or Zener diode as the stabilizer, right? Now, voltage regulator is an electronic circuit, okay, that provides a stable DC voltage independent of the load current, temperature, and AC input variation, right? Mean the voltage regulator is an electronic device. It gives us a stable DC voltage, maybe of any value, like 3 volts, 6 volts, 9 volt DC, okay, independent of the load current. There's no problem of the load resistance, whatever it is, right? And the variation in, if there is a variation in temperature or some variation in AC line voltage, even then the output remain constant, right? Like this is a Zener diode, and here is a load resistance. Load resistance means the appliances which is connected across the Zener. And here is the input voltage. Now the Zener diode, okay, it gives us here the constant voltage, stable DC voltage, okay, independent of the load current. Load current mean if you change the load, right? If you change the load, there should not be any change across the Zener. At the output should remain constant. It should not change with the change in the load resistance. As well, there should not be change in the output voltage if there is any variation in the input voltage, or if there is any variation in the temperature. So this is the meaning of the regulator. This is a supply. Now looking here, okay, this is PN junction diode characteristics curves. Here is the forward biasing curve. Here is the reverse biasing curve, right? Now, the Zener diode works in this region. This is the region for Zener diode. Like here, for example, this is a Zener diode and NP, okay. Then a series resistance RS. Input voltage is connected here. Now one thing to be noted, the positive voltage is connected to the N and negative is connected to the P. That means reverse biasing. That means this region. Okay. Then here is the load resistance at the output across the Zener. Now, what is the special about this region? The special is when the reverse biasing is increasing, reverse bias voltage is increasing, okay, a voltage, then the current will be very, very small in microampere because current is very small. But reaching at this point, suddenly what happens, there's suddenly a sharp rise in current. And what happens here, breakdowns takes place. And this breakdown is Zener breakdown. There are two types of breakdown, Zener and avalanche breakdown. But if the PN junction is heavily topped, first breakdown happens at the Zener voltage. So this is a Zener breakdown. So when the Zener breakdowns takes place, what is special? The special is voltage here, the remain constant, which is called the Zener voltage. The current is increasing. There is large change in current, but the voltage becomes constant. The voltage across the Zener diode, here is always constant, and it is equals to the breakdown voltage, whatever it is, because breakdown voltage is different from the different Zeners. A Zener that breakdowns at 5 volt, suppose a breakdown is 5 volt, will have 5 volt across it. Even if you apply, it remain 5 volt, even if you apply here, the 12 volt. You apply 12, here the output remains 5. If the Zener breakdown is 5 volt. Okay. And what happens? Where is the remaining 7 volt? 7 volt will be here across the resistor. Okay. And if the input voltage is 10 volt, what happens? This output Zener breakdown voltage remains 5, and rest of the 5 appears across the series resistance. So any load parallel to the Zener diode will have that constant voltage 5 volt, okay, across it. Hence we get a constant voltage source. This is how we understand the working of Zener as the constant voltage source. Now here is a Zener diode, and this is a load resistance. Here is a supply, and supply is given to the Zener with a series resistance R. Supply is given to the Zener with a series resistance R, and across the Zener there is RL, and there is an output voltage. Now from here, the current starts flowing I, okay. Now current I is flowing, I passes to R, but when you will reach here, there are two paths for the current to go. Along this, the current divided into the two parts. I'm not saying equal parts. The current will be different through this line and this line. The current divides itself into the two parts. Now, the current flowing through the Zener is IZ, and the current flowing through the RL is IL. So current is now equals to IZ plus IL. This is our first equation. Now there are the two cases to discuss. Number one, the supply voltage V is constant. There is no change in V. We assume that V is constant. And this case is RL is varying. So if the variation is in RL, how the output remain constant, this to see. So if if there is variation in RL, it directly implies the IL will change. Okay, IL is varying. Now this is the property of the Zener diode, that the voltage across the Zener remain constant. So Vz equals to constant. This is the voltage across the Zener. So let me take this path and we write the Kirchhoff's law. How this we are taking this path. Okay, the voltage V, which is the supply voltage, this V builds up across the series resistor IR, and this voltage builds up across the Zener. It is equals to Vz. So V is divided into this part and here across the Zener. So V is equals to IR plus Vz. Now the next is we are taking the change. Delta is attached with every term. Delta V, delta IR, delta Vz. Delta means change. Now because V is constant, we assume that first case there is no change in V. There is no change in V means delta V equals to 0. And secondly, Vz also constant here. If Vz is constant means delta Vz is 0. No change in Vz means delta Vz is 0. What it implies? Delta IR equals to 0. And R is taken out, R into delta I equals to 0. So now I is equals to what? Iz plus IL. So I equals to Iz plus IL. Now multiplying each term by delta, that is delta I equals to delta Iz plus delta IL. Now delta I equals to 0. R cannot be equals to 0. It implies delta I equals to 0. Delta I equals to 0 implies delta Iz equals to minus delta Iz plus delta IL equals to 0. It implies delta Iz equals to minus delta IL. So here it is equals to 0. So it implies delta Iz equals to delta IL. Hence, any change in the load current, is adjusted by the Zener so that the output remain constant. Now it means like if you change RL, with the change in RL, IL will change. Definitely IL will change with the change in RL. If IL changes, what happen? Because change in IL is negative of the change in IZ. Mean if IL increases, then IZ will decrease. If IL decreases, IZ will increase, so that there should not be any change across the output, across the Zener. So in this way, the Zener adjusts the current. Zener itself adjusts the current, okay, so that there should not be change in across the output. Now let's discuss about the second case. Now in the second case, RL is constant. We assume that RL is constant. That means IL is constant. If RL is constant, it implies IL constant. And now let the V is variable. Okay, and our equation is V equals to IR plus VZ. Now here it is V. V equals to the voltage developed across R plus the voltage across the Zener. Now multiplying each term by delta. Delta V equals to delta V equals to delta IR plus delta VZ. Now the R is taken out, delta I plus delta VZ. This is 0 because voltage across the Zener. They remain constant. VZ remain constant, therefore delta VZ is 0. So delta V equals to only R into delta I. Okay. Now what is I? I equals to IZ plus IL. So IZ plus IL. So it implies delta V becomes R delta IZ plus R delta IL. Now we already said that the RL is our constant, or IL is constant. So delta IL, no change in delta. Delta IL is 0, that it implies, because IL is constant. So it implies that delta V equals to R into delta IZ. Hence, so what this equation implies, any variation in V will be compensated by the Zener current. Okay. Input voltage variation is compensated by the Zener diode. By adjusting, it adjusts its current, which is passing through it, so that the output remain constant. So this is our second part, how it happens if there is change in the input voltage, how the output remain constant, because the Zener current is compensated. Zener current compensates the variation in the input voltage. Okay.